Hello, good morning, good evening, whatever time you're watching this. Welcome back. Uh, we're getting into 8.2. We're gonna also do a little bit of 10.1 at the back of this, slash 10.1. It'll be clearly labeled though. Um, there's gonna be a lot of FRQs in this note or in this notes packet that we skip or leave for in-class practice. Trying to keep the video of a reasonable length. I'm gonna get my phone out, make sure we are. So ideas we'll be introducing how do we estimate a proportion. Now remember, a proportion that's p, some number of people who meet, individuals who meet the quality, the classification, the characterization, divided by the total number that you talk to. Estimating in this class means that we're going to make a confidence interval. And if you'd go ahead and write that down, I want you to connect those words together in your mind. Estimate, estimating, time to estimate something. That means it's time to generate a confidence interval. And as a reminder, a confidence interval gives us a range of plausible values. The whole idea is we're going to take a sample and say, okay, let's assume this sample is well representative of the population. And we took it in such a way that we think we did a pretty good job. Okay, and we get a value from the sample. We get our estimate of what the proportion is by saying this many people said yes, we talked to this many people. Great. Could be corn plants, could be rockets at the rocket assembly plant, could be whatever's, right, that meet some condition. Okay, so that's going to be at the center of our estimate. We're going to talk about what's on the back end here in a moment. What type of data deals with proportions? That would be qualitative data. Data, yes, no, 0, 1, up, down, whatever. Some sort, it happened or it didn't happen. Okay, what's the difference between P and P hat? I'm going to put this up here. P is your population proportion, and P hat again would be your sample proportion. So our sample proportion we use to estimate our population proportion. Right. So I left some room there because I want to really talk about this formula for confidence intervals, because I don't think I did it justice last time. I wanted to wait till we had some numbers. When we're making a confidence interval, we start with our point estimate. That is our estimate from the sample. That's our best guess. It's like, we're going to start here. Okay. We don't know P. We want to estimate it using P hat. Remember, the whole idea here is we're estimating P using our P hat. And some other information and some assumptions about these distributions. Those ideas from chapter 7 about sampling distributions of sample proportions. Once again, vocab from chapter 7 is not going away. You should recognize a lot of this looks like 7.2, because it is. So our point estimate from the sample, that's our best guess. Where is it? Okay, critical value. Well, the critical value is an interesting one here. The critical value you see here is a z star. The critical value is going to be, listen with this, and I'm going to write it down. How many standard deviations away do we need to look to be so confident? You remember yesterday from the empirical rule, I talked about, okay, 95% confident. We need to look 2 standard deviations away. I lied a little bit, but you remember we're going to be saying, okay, how far do I, if I'm centered this far away, if I go this far away, how much of the normal distribution have I captured? And I'll draw some pictures for that in a moment, don't worry. So critical value, that's going to be how many standard deviations away will we look? And our standard error is our best guess of the standard deviation from the sample. Because we don't know the actual standard deviation of the population. We don't know sigma. What this is, this thing right here, is the standard error of P hat, which is our best guess for sigma of P hat. Sigma of P hat has P in it, square root P, 1 minus P over N. We don't know P. That's the whole point here, folks. We don't know P. We're trying to figure it out. We have a P hat. That's not P. So our standard error of P, that's our best guess for sigma of P hat. So we're saying, okay, we're going to start here. And we're going to say, okay, I know if this is normally distributed. That's a big assumption here, guys. That normal assumption, back from 7.2, big here. Because that's what's going to allow us to say, okay, if we look this far away, because I know this thing's distributed approximately normally, I can be so confident that I'm going to capture the truth some percentage of the time. So we need to figure out, okay, well, where do these critical values come from? That kind of sounds like a pain to find. This critical values, go to table B on your formula sheet, go to the very bottom. I'll zoom in on this in a moment. Go to the infinity row, and this is the one time you're allowed to write something on your notes. Down by that infinity, you can put a little Z star. And the idea here is this is, once again, how many standard deviations away to look to capture the central whatever percent of the normal distribution. And we've talked about one of these values before, or we've actually approximated it. One we're going to see most often, and I'll look at this in a moment. We talked about the empirical rule told us we had to look about 2 standard deviations away to find the central 95% of the data. I've been lying to you folks. It's actually 1.96 standard deviations away. If you go negative 1.96, positive 1.96 on your Z table, you could do a norm CDF to justify this. You would find that you have captured 95% of the data in there. Where can we find that on our table? Let's switch shares for a moment. We are going to look at my screen where we have this, our formula sheet. We look down at the bottom here on that infinity row, and you're going to see some numbers we're going to use all the time. And the idea here, folks, and you should draw some of these pictures, I'll draw one here for you, is that these numbers here tell us the negative z-score and the positive z-score, such that if we go to them and we shade the area between them under this curve, we're going to find C% of the normal distribution. And that's what we see up here. Our most common values are going to be 1.96 going along with 95%. Sometimes we see a 90% interval. Sometimes we see a 99% interval. Honestly, those are probably your most common 3. If you know 95 by heart, that's going to really help you. So the one thing you are allowed to write in your formula sheet, which I won't get mad about, is if you put a little Z star down at the bottom there. You'll notice up at the top it says T distribution. You say, why are we looking at the T distribution for Z and normal distribution? Yeah, we'll talk about it in a moment. So draw that picture. Hopefully you have that. The idea, we're going to use 1.96 most often, but the idea is, okay, if we do this, 95% of the time we're going to get a value in here. And so that means 95% of the time our value is going to be within 1.96 standard deviations of the true value. Okay, but this doesn't work every time. There is some probability that we could get a value out here or out here in our sample. And then our confidence interval would be wrong. But we said at the front that these confidence intervals don't always get it right. Sometimes they get it wrong with some known error rate. Let's get back to it. All right, so we have a little bit in mind now about the logic of these things. Think back to 7.2. This is a normally distributed thing. That's what Z star means there. We're starting here as our estimate. We're saying we're going to look this many standard deviations away to be whatever percent confident. And if we look further away, we're going to be more confident. It might make the interval less useful in terms of its predictive value or its informative value though. Just think of Garfield. And then we got our best estimate for how spread out this distribution is. Remember, we don't know P, so we got to use P hats here. So that's our standard error of P hat. That's our best guess. That is our estimate of what the standard deviation of P hat is based on our sample data. Using that, we're going to construct our first interval here. And we're going to talk to you finally about this thing I've been like vaguely mentioning the whole time, the 4-step process. State, plan, do, and conclude. I'll do one of these with you. But the idea is we're going to state what parameter we're interested in estimating. We're going to find the variables. That's kind of the state step. The plan step is to check the conditions. The do step is to do the thing. And conclude is to interpret the thing. We'll talk more about this. I'll do some examples of this here in a moment. We're going to do this thing called the 4-step process, stating what are we about to do? Planning. What's the process we're going to use, and why are we justified in using this process? Why are the conditions met? We're going to do the thing. We're going to churn out the numbers. And then we're going to say what this interval means in the context of the problem. That's what I was talking about first day of the course. When I said 3/4 of this course is writing about the number that you are going to find or then did find. Only 1/4 of this process is math. 3/4 of this process, justification, logic, backing up your reasoning. So, polling agency showed the following 2 statements in a random sample of 1048 adults in the United States. And I see 1048 and I think, ooh, that's little n, the sample size. And we got an environment statement and an economy statement talking about which should get priority over which. The order was randomized because if we always give the same statement first, maybe that influences people. Who knows? I don't know. We randomize it though to hopefully eliminate that possible source of bias. Assume the conditions for inference are met. Construct and interpret a 95% confidence interval. So I'm going to circle 95 and I'm going to put CL by it. That's my confidence level. 95% confidence interval for the proportion of all adults in the US who would have chosen the economy statement. So economy statement's right here. So that makes 37 our p hat. That's our sample proportion. That's our best estimate for what the true proportion of people who would have chosen the economy statement is, 37%. But do I think 37% is exactly right? Probably not exactly right. It's probably, maybe it's close. How close? I don't know. But if we look some known distance away, calculated using this data, maybe we could say we're this confident, 95% confident that it's somewhere in here. Could be wrong, but we've looked far enough away that we say this works 95% of the time. Let's go through with that process. Let's do a state plan, do conclude on this. So part A, state. We're going to construct or calculate P. Again, the proportion of US adults who favor the economy statement. We don't know P for the whole population. We took a sample. The sample said 37%. We don't know about the whole population. Our plan here is we're going to construct and I forgot to highlight it back here. This thing is called I didn't even name it. This formula back here is for a 1 sample Z interval for a proportion. Go ahead and write that down. I'm going to highlight it because it's important that it be noted. This is a 1 sample Z interval for a proportion, and we need to be able to name this process. 1 sample, we took 1 sample. We're constructing an interval that relies on a Z statistic, a statistic under the assumption of normality, okay? And we're doing this for a proportion. So the name tells us about what we're about to do here. That's nice. So we've stated proportion of US adults who favor the economy statement. Plan, we're going to do a 1 sample Z interval for P. In your calculator, this is called a 1 Prop Z Int. We haven't done it in your calculator yet. I'll show you that in a minute. And we were told to assume conditions met. We don't always get to do that, but apparently now we get to say random, normal, independent. Apparently, magically, all met. Great. That is a big savings of your time because that conditions check is not always so easy. And sometimes you got to go through, the checks. Did we take a random sample? Now he's even going to talk about it. So why did he even save us time? Take a random sample size less than 10% of the population, and our successes and failures, our observed successes and failures, both at least 10. Take a look back at the end of 8.1 notes if you forgot what I'm talking about, or even 7.2 notes. So we've planned. Now we can go ahead and do. The do step involves calculating the thing. Again, this is going to be p hat plus or minus z star square root p hat 1 minus p hat over n. Plug things in there. That becomes 0.37 plus or minus 1.96. Remember, that's the value we looked up earlier for z star from our critical values table there. Square root 0.37, 0.63 over our sample size of 1,048. Okay, so what is that? That's our point estimate. That's our margin of error. Let's calculate our margin of error separately and write it down. We're not always going to do it this way, but for the sake of this one, we will. 1.96 times square root 0.37 times 0.63 divided by 1048. I do that, wham bam, and that's 0.029. How many decimal places? Let's call it 0.03. Make our life nice and easy. So 0.37 plus or minus 0.03. Turn off my lamp. And all right, so now I'm telling you we're looking 3% away. So our final interval is 0.34 to 0.40. That's our confidence interval. And so now for the conclude statement, we regurgitate our template. We are 95% confident that the true proportion of U.S. adults who support the economy statement is captured by the interval 0.34 to 0.40. We are 95% confident that the true proportion of U.S. adults who support the economy statement is captured by the interval 0.34 to 0.40. Again, search that, AP Statistics, scoring guidelines, cut off the number 5, scroll the number 5, you'll find the answer there if I ever go too quickly or you're unable to pause and see something correctly. So we can calculate a confidence interval, and that's really it. The rest of this is some algebra with sample sizes and showing you how to do this in calculator. So this is not bad. A lot of people like this. It's very formulaic. State, plan, do, conclude. All right, there in part B, we haven't looked at that. One of the conditions was that both the number who choose the economy and who don't choose the economy are both greater than 10. Explain why it's necessary to satisfy that condition. That is the normal condition. Allows us to approximate p hat distributed normally. It allows us to assume that p hat is distributed normally, and then that allows us to use our z star critical values in the confidence interval. Great. So we can make these confidence intervals. Most of it is going to look state, plan, do, conclude in part A, and part B is going to be like, hey, what about this condition? Or hey, what if we did something a little different? What if this hadn't been met? What if this was a problem? Right. So a lot of people really like these. They get formulaic. State, plan, do, conclude. Hopefully we can do this. I am going to leave the soda as an example. Save as the in-class practice. When you're in class, when you get to this, if you want to do it with me, throw up your hand. I'll do it with you. I'll sit there and do it with you. But we're going to save that. I don't want to put that in the video. Save that for an in-class practice sometime, maybe for review day. Sometimes we want to calculate margin of error. When you really do, you're taking a poll. You want your poll to have some margin of error, plus or minus. I don't know. You ever watch the news? It's usually about 3%. Right? They like to keep it within 2 or 3%. Margin of error, that's how far away you're looking. Remember how far away we look from our point estimate. All right, that's like the width of our net, or half the width of our net. How far away am I looking? Margin of error is that part out back, the z star plus or minus the p hat, square root p hat 1 minus p hat over n. Sometimes we need to calculate for a given margin of error. And again, this is the hardest algebra we're going to do in this course. Sometimes when calculating for a given margin of error, we have to do a little bit of algebra to solve for sample size. So what are we really doing here? Solving for n. Determine the sample size, need to estimate p within 3% with 95% confidence. Up top here, reminder, this p is unknown. We're going to use the most conservative value of p equals 0.5. So what are we saying here? Determine the sample size. Okay. Estimate within 3%. So 3%, that's my margin of error. 95%, that's my confidence level. So what I'm saying here is my margin of error z star square root p star 1 minus p star over n. That, I'm just going to put hats on those. It's fine to put hats. We need it to be less than 0.3. So we're going to put 0.03. The z star associated with 95% confidence is 1.96. Square root 0.5, 0.5 over the thing we're ultimately going to try and solve for, which is n. And this is the hardest algebra we have to do all year. Can you solve for n? Hopefully. Take a moment. Do some algebra. Can you do it? Let's do it. Divide by the 1.96, 0.03, 0.96. All right, that's need a square root. Square root of 0.5 squared over n. That's cool. So I'm going to move that up, move that down. This is going to end up being, well, do you want me to do every step? I'll do every step, guys. I'll square both sides, and this becomes 0.03 squared over 1.96 squared, greater than equal, still 0.5 squared, square the square root, whatever, over n. Solving for n, moving that up, moving everything else down, n greater than equal 0.5 squared, 1.96 squared over 0.03 squared. Make sure you can do that. $1067.11. N greater than equal 1067.11. So how many people we got to talk to? 1,067.11 people. How do you talk to a 0.11 people? Round that up, round up. N greater than equal 1068. Call it. Put a box around it. So we can do some margin of error calculations as well. And those aren't bad. Those show up more often in a multiple choice setting or as a part B on a part B or part C on a free response question. And it just so happens I have one that shows up on a free response question. Let's do a little more complicated one. I'll pause for you on this one and let you try it without me just working through the whole dang thing. Make sure you can do this algebra, folks. Don't kid yourself on the algebra. We've seen this one before. We saw it in yesterday's notes. Let's pause, take a look, try this yourself. So this one's a little more challenging, right? Because you got to kind of like, well, what's the challenge? Being able to pull the details from the dang prompt. That's the challenge. You had to see that 95% is your confidence level. That's going to go along with the z star of 1.96. You had to see that your p hat is 0.417. That's your point estimate. 41.7% of the sample. And your margin of error 11.9%, 0.119. You had to label that, and you were to say, I don't know n. Don't know it. So you had to set up a formula that relates all those things. Margin of error is z star plus or minus p hat 1 minus p hat over n. That's just that right there. That's the margin of error. Excuse me. Plug everything we know in and do a little bit of algebra and see that it's got to be 66 households. So there, margin of error. Hopefully we can do that. Good stuff. I've got some more examples here that we are going to skip around. Example 2015, number 2. We are going to save this. We're going to save this as in class example. I'd like to do that probably, next time I see you in class. We'll do a couple of these together. And the last thing I want to look at before I think we pop along, we've got a lot of examples we're skipping here, by the way, is how to do this in calculator. You'd love to do this in calculator, right? It's called a 1 Prop Z Int. The nice thing is it only requires 3 things. You got to tell it X, the number of successes, N, the sample size, and our C level, obviously your confidence level. I don't know how to write that even more succinctly. Does it for you. So where is this? We go clear, clear. Ooh, what are we doing? We're going to stat, going to tests. We're going down to 1 Prop Z Int. That's option A. See up here, option A, the 1 Prop Z Int. And what do we put in there? We put in there 3 things: the number of successes, sample size, and it spits out an interval for you. This does the do step for you. Feel free to use this. And then we have a couple more examples dealing with what this looks like. What this looks like in free response questions. I don't know that I want to show you all these. I might show you one here. Let's do one. And then we'll skip to the 2 sample stuff and we'll call that good. So we're going to put it all together here. We'll do this one using the calculator. Oh, how topical. This is not a plant. During a flu vaccine shortage in the United States, I didn't even plant this here. It's just here. It was believed that 45% of vaccine-eligible people received the flu vaccine. Gosh, how could we skip this? The results of a survey given to a random sample of 2,350 vaccine-eligible people indicated that 978 out of 2,350 received the flu vaccine. I won't even say it. Get your gosh dang vaccines. God. Construct a 99% confidence interval for the proportion of vaccine-eligible people who received flu vaccine. Use your confidence interval to comment on the belief that 45% of people had received the flu vaccine. Comment on the belief. So we're going to make a 99% confidence interval. We've got an X, the number of successes. We've got an N, our sample size. And we've got a belief. I'm going to circle that 45%, and I'm going to write a little null hypothesis here, is that our proportion is 0.45. That's our null hypothesis. So that's our one of our first null hypotheses. Don't worry too much about that notation. Somebody believes that. So we got a little confidence interval part in the first, and we got a little sample size in the second. So construct a 99% confidence interval. State plan do conclude. State. We're calculating P, the proportion of vaccine eligible people who received it. Great. That's all we have to do in the state step. Our plan will be to construct a 1 sample Z interval for P. And then we're going to check the conditions for that. We took a random sample of 2,350 people. Do we have normality? Well, we had 978 successes, which is greater than or equal to 10. And 2350 minus 978 is, what is that? 1372 failures, which is also greater than or equal to 10. So that meets our normality condition. And we have independence. We have to have at least 10n, that is 23500 eligible people, which we certainly do. So our conditions there are met. So we had our name of the test or the procedure and the conditions. We have our parameter up top here. So we defined our parameter. We say, what are we going to do? We say, why are we justified in doing it? So again, state, plan. Now we can go ahead and do. And we're going to do everything in our calculator on this one. This one sets up really nice for calculator work. So we go back here. We go back stat tests. We go down to option A. If you want to use your alpha to get down there, you can. 978 out of 2350. Guys, this is literally all you have to do. This is so don't worry about using the formula because it just does it for you. This class is not about your ability to run numbers through a machine. It's about your ability to like justify processes and interpret what the numbers mean in the end. So, you know, let's worry more about the interpretation. We'll write this down. Let's round to 10th. Well, let's go out 3 decimal places. So 0.390 and 0.442. Okay, so 0.390 to 0.442, and we say, okay, that's literally all we have to write. If you wanted to, you could have said 1 Prop Z Int out to the side, and you could have said X is, you don't need to do this. N is 2350, and C level is 0.99. Doesn't hurt my feelings if you write all that down. It's going to help me diagnose any issues you have. Get in the habit of writing everything you put in a calculator down. So that's our lower bound, upper bound. Conclude. And I'm probably going to skip part B for the sake of time here. Yeah, maybe I'll do it. I don't know. We'll see. Conclude. You know, try this yourself. We are 99% confident that the true proportion of vaccine eligible people who received the vaccine is captured by the interval .390, 0.442. Okay. Now what about our 45% thing? Since 0.45 is not in that interval, it is not plausible. So we can doubt the claim. Cool. That's all I have to say. And then for part B, it's a sample size problem. You do it. It's more sample size calculations. I'm not as worried about that one. Again, you can go to 2011 Form B, find the answer to this. Another margin of error problem. If you haven't been able to do the algebra on the last two, do it again. Do part B, and make sure we can get a square root, a variable out of a square root in a denominator. Okay. So what else we got here? I am going to save another one of these, 2010B number 4. We're going to save for extra practice. You see that's the end technically of the 8-2 notes, and then that takes us to 10-1 comparing two proportions. I'm not going to spend a ton of time talking about this, folks, because you're going to see that it's essentially the same. You can read all this if you want. I'm not worried about it. Just look down here at the bottom. There's a bunch of reading up there that I'm not as concerned with. I'm down here at the bottom. This is a confidence interval for P1 minus P2, a difference in proportions. Two sample Z interval for excuse me, those should not have hats. Get rid of those hats. For P1 minus P2, for a difference in proportions. It's the same formula. But instead here it's P1 hat minus P2 hat. And this looks like something from, that looks like something from 6-2 combination of random variables. That's the standard deviation of a difference of random variables. Because what is this? The difference of random variables. What is this? The standard deviation of that difference. Take a look at your 6-2 note cards. Heck, it's still here on the board. I'm looking at it right now. Combination down at the bottom. That formula I forgot when you get to the apples problem. So what do we have to do here? Really, we're just applying the same formula. I really only have one example here, and it's just not that different. Same sets of assumptions. You see here, random, normal, and independent. We just got to check the independence question twice and the normality question twice. All failures and successes at least 10. But really here, I'd just like to show how we'd quickly calculate something like this in our calculator. We'll do the setup here. As part of the Pew Internet American Life Project, researchers conducted 2 surveys in late 2009. They asked 800 US teens, so it's going to be N1, about their use of social media and the internet. A second survey posted a similar question to 2350 US adults, so that'll be N2. 73% of teens and 40% adults, so that's like P hat 1 and P hat 2, said they use social networking. Use these results to construct and interpret a 95% confidence interval for the difference between the proportions of US teens and adults who use social networking. So our state would be, P1, the prop of teens on social networking, and P2 will be the prop of adults on social networking. Those are ditto marks. You can feel free to use them if your proportions are, talking about the exact same type of thing. Our plan step, making boxes now apparently. Our plan step, we're going to do a 2 proportion Z interval for P1 minus P2. That'd be sample. 2 sample Z interval for P1 minus P2. We're going to estimate the difference in these 2 proportions. Still got the assumption of normality, and now we're just using a little bit from 6.2. If you want me to justify this with the 6.2 logic, I can. You just don't need it right now. So the plan 2 sample Z interval for P1 minus P2, and we're going to do a little random sample, was told. We need to check that N1 P1 hat, N1 1 minus P1 hat, N2 P2 hat, and N2 1 minus P2 hat are all at least 10. So let's do that. We're not actually given the number of successes and failures, so I got to do a little bit of math. 800 times 0.73, that gives 584 said yes. So that leaves, what is that? 216 said no. Second part, 2253 times 0.47. Let's round that up to 1059. And a little bit of arithmetic tells me that's 94. And these are all at least 10. So we have normality. And then we need independence. And there are clearly more than 10 and 1, 10 and 2 US teens and adults. So our plan step has us naming the test, and I'm sorry, I'm just going to rewrite that. That says sample z interval for p1 minus p2. We check that a random sample was taken. We check that the conditions for normality are met, and we check that these are approximately independent samples. And then we go ahead and do it. The do step, again, is a pretty easy part. That's why I'm really doing this problem, so I can show you how we put this in our calculator. So you go stat tests. We're doing a 2-prop z interval. How many successes were there with the teens? 584 out of 800. How many successes were there with the adults? 1059 out of 2253. Confidence level, we're told 0.95. Oh, that did it. I hit enter too quick. Try that one more time. You don't have to put any numbers in again. It gives it all right back to you. All you need to write down there is just everything it tells you that you haven't written down already. So I'm going to turn off my lamp, and I'm going to write down my final interval, 0.2229, 0.2970. And I might write P1 hat is 0.73, P2 hat 0.47. And so then we have one last thing, which is our conclude. We are 95% confident that the what? The true difference in proportions of US teens and adults is captured, and I'm running out of space. But here I want to note true difference in proportions. We're talking about a difference in proportions here, P1 minus P2 in this case. I believe that that's all I want to talk to in 8.2 today. We've got a bunch of examples left today, a bunch of problems that I have said extra review. We will do those at some point or another. There's one of those I want to do the next time you see me in class. I think that was the first one. Make note of that. Have me come over and work through a confidence interval problem without, not on the video, but like in person. Can you imagine it? So see you next time. 8.3 next time. Take care of yourselves.